right, so it's going to be a pretty long video, so hopefully you guys are ready. All right, we're going to do all of these questions, and this is pretty long. I think there's like 19 or 20 multiple choice, and then a free response, so a lot to do here. So here we go, start with number one. Let's just run through it. All right, so it says, suppose a person was having 2 surgeries performed at the same time. If the chances of success for surgery A, so the first one, are 85%, and the chances of success for surgery B, the other one, are 90%, what are the chances that both would fail? And this is what Marilyn did. So let's just take a moment and think, how did Marilyn find the 0.15 and the 0.1 numbers? Complements, right? So if you have an 85% chance of success for surgery A, then you have a 15% chance for failure for surgery A. Okay, same thing for surgery B. And then what did Marilyn do with those 2 numbers? She multiplied them, right, to get 1.5%. But here's the deal, guys. It's been a long time since we've done chapters 14 and 15, okay, probability. And in that chapter, we did a multiplication rule, but there was something we assumed independence to do this multiplication rule. All right, and here's the deal. I mean, I don't hopefully ever want to have to do 2 surgeries at the same time, but do you think that these are independent of each other if they're operating on the same person at the same time? Probably not, right? So if you tell me surgery A has failed, then I'm worried that surgery B is going to have a higher chance of failing as well. So what I'm looking at is answer E, because she assumed independence, which in this case I think would be wrong. Yeah, it's the same person. It doesn't say anything about who's operating, right? It could be different surgeons, but with the same person, that worries me. Number 2. So we've got a letter. A woman lamented that she had just given birth to her 8th child, and all girls. Whoa. Her doctor had assured her that the chance of the 8th child being a girl was only 1 in 100. What is the real probability that the 8th child was a girl? Any thoughts? Don't think so hard. It's actually B.
Oh my God.
Because the likelihood of a boy or girl is 50%.
Wait. Is this an AP question?
No, it's just basically saying like you're going to even if you had 4 girls in a row, the chance of you having a boy or a girl is still 50%. Yeah, go ahead.
How do you know that they don't mean it's what's the chance that you had 7 girls and then another?
Good question. It would say what's the probability that the 8th child is the first girl. That would tell you that they had 7 boys.
Or the first boy.
Yeah, exactly.
Okay.
Yeah, that's how they would say. You're good. No worries. Yeah, that's not an AP question. You're right, Joseph.
So it's not.
Yeah, don't worry. I'm just trying to get some of these questions I put on here. It's less about the answer and more about what we can talk about as we answer it. All right, here we go. We actually did a question with this same mortality rate for prostate cancer back in the day in the first semester. So it's 25 out of every 100,000 men. So this is the probability of dying from prostate cancer. All right, so dying, and this is men from prostate cancer equals 25 out of 100,000. So if you need to take out your calculator to do that division, so 25 over 100,000. This is the likelihood of that person dying or that man dying from prostate cancer. So no, it's not A. They're trying to get you to pick A, Carolina.
C.
Okay, well, let me do the problem first. I'm just trying to take a sentence that I read with words and turn it into a probability. Okay? Now it says we have a group of 100 American men. What is the probability that at least one is going to die from prostate cancer in a given year? So that'd be 1 out of the 100 die from prostate cancer, or 2 out of 100, or See where I'm going with this? At least one, so 3, 4, like all the way up to 100. All of them die of prostate cancer. So what I've tried to teach you guys when you see the words "at least" is to think of this as like a special case. Remember how we did this in the first semester? No, it's that C word again.
I remember. It's that C word?
It's the complement.
Oh.
So what I'm going to do is ask myself, go ahead, Zima, is what is the complement to at least 1 out of 100 dying of prostate cancer? No? Did you say no, straight? No. So it's asking, what's the likelihood that at least 1 out of these 100 men dies from prostate cancer? So that'd be 1 out of 100 could make that true. 2 out of 100, 3 out of 100, 4 out of 100, 5 out of 100. See where I'm going with this? So what's the number I'm not saying? 0. So the complement to this is 0. So what I'm going to do to find at least 1 is do 1 minus the probability of none of them die from prostate cancer. And this is how you want to do it on the AP exam.
At least when you see the word at least.
When you see that word at least, you're thinking complement. All right? All right, so you guys ready? So this is the probability of dying from prostate cancer for a man. Everybody okay with that? All right, so when I say probability that none out of 100 are dying, I first need to figure out the complement to this. So if this is my likelihood of dying from prostate cancer, what's my likelihood of dying from not prostate cancer? 1 minus that, right? I'll put that over here. I can put it under. So not. All right, so 1 minus 0.00025, right, which is 0.99975. Okay, so it shouldn't surprise you. What's my likelihood of dying from something other than prostate cancer? Pretty much it's most likely I'm going to die of something other than prostate cancer. Okay, that's true for all men. Now, I'm going to put that here. Right? Put that there. Because, and then I need to raise it to some power. No? Do I need to go back, Caroline? So I'm trying to do this in a couple of steps. The first step I did was taking the first sentence and putting it as a decimal. Okay? Then, if this is my likelihood of dying from prostate cancer, this is my likelihood of not dying from prostate cancer. So this subtracted from 1. So to find what it's asking, the likelihood that at least 1 out of 100 American men will die from prostate cancer, I find the complement of that, which is that none out of 100 are dying. So here's none, right? But to make it out of 100, that means it's this times this times this times this times this. How many times? 100 times, because every man has this likelihood of dying from something other than prostate cancer. So we're going to type this in the calculator to get our answer. 1 minus 0.99975 raised 0.0247. The answer is B. Yeah, Thomas.
Could you repeat one more time why we went to
Yes. So maybe I can write this to help. So none out of 100. Right? So that means the first man did not die from prostate cancer. So this probability right here. Okay? The second man, same thing. So it's this and this and this for all 100 men. So that's why I did this to the 100th power, because you're taking this probability and multiplying it by itself 100 times.
So you're going to buy the same.
Correct. If this had said 1,000, it would be 1,000. All right, ready? Okay, number 4. Suppose that in a certain part of the world, in any 50-year period, the probability of a major plague is 0.39. The probability of a major famine is 0.52. The probability of both plague and famine is 0.15. So I'll just kind of summarize for you. So this is plague is 0.39. famine, 0.52. That last piece they gave us was both of them, right? Plague and famine, which is 0.15. Thank you. What is the probability of a famine occurring given that there is a plague? So they're telling us what has happened. A plague has happened, right? A plague has happened, right? So if we know a plague has happened, what's the likelihood that we're also going to experience a famine? So this is actually a formula from the AP exam formula sheet, and this is what it says on the formula sheet. The probability of A given B, yeah, this line means given. Yeah. So A given B equals the probability of A and B on top over the probability of B on the bottom. All right, so what is my given? What is my given? What are they telling us has happened? No, they're actually telling us, given that there is a plague. You're good. So the denominator is going to be plague. Okay? The numerator is both happening. What is the likelihood that both happen? 0.15. So if I type this into the calculator, I'll get my answer. .385. What's that?
No, we only use that equation with
the moment I see given.
Yeah.
I'm not guaranteeing I'm going to use that equation, but when I see given, I'm thinking that that's an equation I could use. Let's do 5. Okay. It says the probability of event A happening is 0.2. Probability of event B happening is 0.1. Do you guys remember this U symbol? This union symbol, what it means? It actually means or. It means or. The way you want to remember it, Thomas, is the and symbol is like this, and think of it like it's starting to make an A for and. That's how I remember. So this is the probability of A or B. And this is actually another formula you get on the formula sheet. Yes. The formula on the formula sheet says A or B equals probability of A plus B, but minus the probability of A and B, because we don't want to double count. Okay, so we're trying to find the first thing. Do we know A? Yes. Do we know B? Yes. But what about A and B? Do I know A and B? No. But do you know the formula to find A and B? You multiply them, but you have to assume what? Independence. Oh my goodness! It says A and B, those events are independent. Sick. So A and B is multiplying them together, 0.02. So this will be 0.2 plus 0.1, which is 0.3. 0.3 minus 0.02 is 0.28. All right, number 6. All right, we have a warehouse sale. 100 customers are invited to choose one of 100 identical boxes. So do you know what's inside the boxes? No, so you're just picking one, right? 5 boxes contain $700 color TV sets. 25 of the 100 boxes contain a camcorder. And the remaining boxes, that's what, 70 boxes contain cameras. All right? What would you be willing to pay to be able to pick one of these boxes?
Is
What do you
it
think?
just an us question?
No, I mean, there's a statistical way to figure it out. I'm just curious what you would pay.
Are we told like the fact that some will contain like this and that or no?
You're told that you look out into the warehouse, right? Can you imagine the warehouse?
Yeah.
There are 100 identical boxes, and they're taped. So you have no idea what's inside them. And they say, okay, you want to pick one? It'll be this much money. How much would you be willing to pay to go out there and pick one box?
They're all the same price?
You're paying me the same price. But you might get a TV set worth this much. But you might get a camera that's worth this much. We don't have to say around. I mean, like, what price would I charge? Do you think if I'm the person in charge of this?
The answers right there.
Does that mean
Well, it's there, yeah. How would I find a charge to? It's B? How do you know that?
It's B or C.
Can we do some math here? Any thoughts?
do you
I feel like B is just fine.
Multiply.
Oh, I don't know. Just multiply. Okay, my guess is like the 5 boxes times the
Okay.
price or something like
Yeah, okay. So I heard times the price, so $700. Now, I'm not going to write 5 because it is 5 boxes, but it's 5 out of how many boxes? So what's the likelihood of me getting one of those boxes? 5%. So I'm going to multiply 5% times that. Okay? Plus. .25 times 540 for the camcorders. And what about for those cameras? 0.7 times 260. Do you know what this is called that we're doing? When you multiply the probabilities times their prices and then added them all together? It is a statistic, yes. It's the mean, it's the average price, or you could say it's the expected value. Expected value. All right, so what is it when you get that? So if you're a person who's walking up to this warehouse and they say, hey, you got to pay me $400 to go do this, are you going to do it using statistics?
Yes.
No, you're going to say, no, that's too much.
Oh.
What if they say, you can go out there, but you got to pay me $100? You're doing it, right? Because most likely you're going to, well, I mean, 100 is a bad idea. 300, let's go 300. Yeah, go 300, right? Because there's a chance that you get something that's, you're overpaying, right? If you pay $300, but there is a chance that you are getting a deal on these. And since 300 is less than this, statistically speaking, if you don't factor in anything else of like how much money you have or anything like that, you should say yes. Okay. All right. Let's do 7. Ooh, I really like this question. Okay. You ready? We're going to flip a coin. Hey, Victor! Your stuff should be...
Wait, sorry, I have a question about number 5.
Yeah, go ahead.
I'm sorry.
Don't need to apologize.
It says A and B are independent. Did it give us that information? The answer be E?
It would be. You're saying like there's not enough information?
Yeah.
Yes, that's correct.
Okay.
Okay, number 7. So we're flipping a coin. How many of you guys have flipped a coin before in your life? You never flipped a coin in your life, Carolina? Never in your life? Oh my gosh. Okay, well, hopefully you know that it could come up heads or tails, right? Okay, we're good on that? Okay. Now, if the first game says you win a prize if you flip the coin and you get between 40 and 60% heads. The second game is if you flip your coin and you get more than 75% heads. Well, the way that I view this problem is it's really a question of something called the law of large numbers, right? So let's say I flip a coin right now. Okay, what is it, Joseph? It's heads. All right, perfect. I flip a coin right now. It's hard to do one-handed.
Do it.
Okay, I'll keep track.
Tails.
It's heads. You're wrong. All right. So right now, what is my probability of heads? 100%. Okay. Heads. What's my probability of heads? 100%. Heads. What's my probability? 100%. Heads. Still 100%. I'm not. Heads. That's 5 in a row?
He's lying.
I'm not. Heads again. Are they both heads? No, we're good. That's 6 in a row. Tails. I got one. All right. Let's say this was my 5th one. Or yeah, my 5th one. That's a little easier. All right. So now my percentage of heads is 80%. Okay. So as I do this, if I keep getting heads, it'll obviously take longer. But as I keep doing this, if I do this 50 times, 100 times, 1,000 times, eventually, what's my probability of heads going to start approaching? 50%. So the longer you do it, right, the law of large numbers says we're going to eventually approach this 50%. Okay? So in this game, if you would like to have something that's over 75% heads, you actually want to flip the coin a less number of times. Okay? Because the fewer number of times you flip it, you have a better chance, as you just saw, of getting something that's more extreme. So in this answer, you actually are going to try to pick D, where you flip it more for the first one, because the more you flip it, the closer you'll get to 50%. And you want to flip it less if you want a more extreme answer. Like, remember, I just flipped it 6 times, I think it was. I got 5 heads and 1 tails. That's a small number of flips, though. Okay? Oh, Carolina, you should have done it, because then you could flip a coin. Nice. All right, number 8. We have an insurance company, charges $800 annually for car insurance. Man, wouldn't that be nice? The policy specifies that the company will pay $1,000 for a minor accident and $5,000 for a major accident. If the probability of a motorist having a minor accident is 0.2, and the probability of having a major accident is 0.05, how much can the insurance company expect to make on a single policy? Well, first off, how much money am I giving the car insurance company? $800. All right, so you can see that all the numbers are less because there's a chance I get into a wreck. What is my likelihood of getting into a minor accident? 0.2, right? That's my likelihood. How much are they going to pay for a minor accident? $1,000. All right. What about for a major accident? 5,000, but it's not as likely to happen. All right. So this right here is how much it's going to cost them per year. Right. That's what they're expecting. But again, at the end of the day, I'm already paying them $800. So if I figure out what that is, that could be what they expect to make each year on each policy. So we've got 0.2 times 1,000 plus 0.05 times 5,000. So this is what they're expecting their cost to be. 450, subtract that from 800, and you'll get your answer of 350. This is an extremely simplified version of how insurance works. All right, 9 through 13 is going to use this table. All right, do you guys remember what this table is called? What do we call these tables? Nice, Diana. Two-way tables or contingency tables. Very good. All right. So this was kind of nice. They've given you the totals. You guys see all the totals here on the margins? All right, so that's nice. If you don't have margins, later on in one we won't have margins. Go ahead and take a moment to calculate them. All right, it's worth your time to figure out those totals. So we're looking at the relationship between the essentially attendance, or like skipping class, and your GPA. You probably can imagine if there is a relationship, what do you think it'll be? I would agree. Yeah. Or the more you attend classes, the higher your GPA you can expect, right? So we don't know, but that's what we're thinking. All right. What is the probability that a student has a GPA between 2 and 3? So how many students are there? There are 1,000, right? 1,000. That's the grand total. So that's my denominator. And how many have a GPA between 2 and 3? 475. Notice, do I care whether they are skipping or not skipping? I do not. So the answer is D. Let's do 10. What is the probability that a student has a GPA under 2 and has skipped many classes? All right, so we have out of 1,000. So now I'm looking at GPA under 2, right? So under 2 and has skipped many classes. That would be 80 students. 80 students have skipped many classes and have a GPA under 2. All right, what is 80 divided by 1,000? 0.08. All right, keep going. We're going to use the same table for the next 3. All right, what is the probability that a student has a GPA under 2 or has skipped many classes? So I'm actually going to put my probability here, my formula for or. We've already used this once. Okay. So the first one says under 2. So under 2 would be 255 out of 1,000. Plus, the next one is going to say skipped many classes is 110 out of 1,000. Right? Now in this one, we're looking for the combination, which I think was that the one we just did in number 10? I think it was. So under 2 and has skipped many classes would be 80 out of 1,000. All right. So what's that? 0.255 minus 0.11, or excuse me, plus 0.11. So that's 0.365 minus 0.08. .285. Here it is again, Joseph. I know you're getting tired. Go to sleep if you need to. No worries. But here it is in number 12. What's that word that you see in number 12? Given. Right? So I'm using that formula again. Actually, you know what? I'm not going to use that formula. Here's why I don't need to use the formula. Because I have the table. All right? So what I just do is I'll write it for you. So my given is what? Skip classes. And we're looking for under 2 GPA. So what I just tell students, if you have the table, is look at your table, right? They're telling us what about this student? What are they telling us is the given about this student? They've skipped many classes. So I'm just going to go to that row, and how many students have skipped many classes? 110. So that's going to be my denominator. And now if I just look in that row, right, just in that row, I'm looking for an under 2.0 GPA, which is 80 out of 110. All right, so there's only one that's over 50%. So E. Hold on. All right, now 13, it's a multiple choice question, but I just wanted to put it on here to kind of review again. Do you remember how to determine if 2 variables are independent? All right, and I'll focus on this one just saying GPA between 2 and 3 and skipped few classes. So what I tell students is pick one. All right, which one do you want to pick? GPA between 2 and 3 or skipped few classes? Which one? I don't care. Okay, so let's do that probability. So this is GPA between 2 and 3. Okay, so go to the table. Out of 1,000 students, what number of students have a GPA between 2 and 3? 475. Awesome. Okay, which is 0.475. Everybody good? Now, here's how you calculate if this event, having a GPA between 2 and 3, is independent of skipping few classes. You copy it again. So notice I'm copying again. But now I'm going to tell you that this student has skipped few classes. All right, so this is the way you want to do it on the AP exam. Pick one, find the probability, then do it again, but introduce the other one as the given. All right, so look at your table. All right, How many students have skipped few classes? 890. Very good. And out of those 890, so just that row, how many have a GPA between 2 and 3? 450. I don't know what that is, so let's calculate it. .506. What do you notice about those two probabilities? They're what? It is, it's true. But what I'm trying to show you is, do you see how they're not the same? If they are not the same, then these events are not independent. They have a relationship. What if those had been the same, or essentially the same, like really, really close? Then they would be independent of each other. Okay? So yes, you're right. It's not independent because those don't match. All right? So essentially what we're saying is that if I tell you they've skipped few classes, so they don't skip school a lot, what do you think is going to happen to their GPA? You think it's going to be a little bit higher. That's what we're saying. All right, keep going. We're almost there. Number 14. What is the probability that a senator is under 70 years old, given, oh my gosh, again, given that he or she is at least 50 years old? So this is under 70, given at least 50 years old. All right, so let's get a denominator. All right, what would be in this table senators that are at least 50? Which numbers would match? Excellent, I agree. So 36, 22, 5, and 2. So all those numbers, those four numbers, I'm going to put in the denominator. Because remember, the given is your denominator. Now my numerator is under 70. All right, under 70. So when you look up there, what am I looking for under 70? Now this is where you got to be careful. So I'm going backwards, right? Under 70. So 22, 36. Why am I not going to include 30 and 5? Exactly, because the given is that they're at least 50. So you only include the 36 and the 22. Okay? So just be careful on that. So this is, what do we got? 36. We can do that one in our head. So 36 plus, I think we do all this in our head. All right, so I'm going to do 58 divided by 65. 0.892. We're so close, guys. We're really, really, really close. I know. This is a long video. All right, another table. All right, this one talking about 500 people used an at-home test for HIV. Then every single one of these people, whether they had a positive test from their home test or a negative one, they went to the hospital to undergo more testing at the hospital. Okay? So they've given us this table, all right, that shows you kind of what happened. So this is all the people that had a positive test at home, all the people that had a negative test at home, right? All the people that actually, when they went to the hospital, had a positive, yes, you have HIV, or this one, you do not, okay? So remember, this is 500 people. So 15, what is the probability that a person has HIV and tests positive? So out of 500, they have HIV and they test positive. So go to positive, and they have HIV, which is 35. Very good. All right? So 35 out of 500 is 7%. Number 16. What is the probability of testing positive given the person does not have HIV? So what's my denominator going to be if it says given they don't have HIV? You go to the healthy column, which is 460. I think it was Diana. So now if I look at the healthy column, right, I'm only looking here, I want to look at what is the probability that they tested positive. So just this column, what number is they tested positive? 25, right? So 25 out of 460. 0.054. That kind of makes sense to me, right? If I know that you're healthy, do I think that you're going to test positive for HIV? Probably not, right? So that doesn't surprise me that that number or that percentage is small. Okay, same table, number 500 still. What is the probability of testing positive given the person has HIV? So how many people do we know from this table actually have HIV? 40. So if I look at just that column, how many tested positive? 35. Again, does that surprise you? No, right? We know that they have contracted HIV, so it wouldn't surprise me that they tested positive. So 0.875. The last one for this one. What is the probability of testing negative given the person does not have HIV? So they don't have HIV, so they're healthy. 460. And how many tested negative? 435. Which is 0.948. Close. Actually, I don't know what the answer would be. They're saying, I guess they're gonna say it's D, but I would put 0.948. Well, because they're probably rounding this to be 0.95. The 7 makes it a 5, but I would do 0.948. Yes. What's it say?
945.
Did I do something wrong? I might have typed it wrong. Oh, thank you. I put 436. Thank you. I lied. 946. I mean, technically they're both right. One's just rounding a little differently. All right, 19. Thank you, Diana. 19. 65% of all divorce cases cite incompatibility as the underlying reason. If 4 couples file for a divorce, what is the probability that exactly 2 will state incompatibility as the reason? Okay, here you go, guys. Ready? This is a long time ago. Do you remember me talking about Bernoulli trials? Do you remember Bernoulli trials? Joseph Bernoulli? No, Joseph. Okay. There were 3 things that had to be true for it to be Bernoulli trials. Do you remember the 3 things? Independent events is one of them. Yeah. Independent events or trials. No. This one always gets kids to chuckle. Constant P. Constant probability of success. And there has to be either 2 options. Success or failure. So in this case, what are my 2 options with these couples? Well, what would it be? They've said they got divorced for incompatibility or something else, some other reason. Okay? So this is a Bernoulli trial. From there, I taught you 2 models. I taught you the geometric model. You remember what key word I used with the geometric model? That's waiting until the first success. So it'd be like, what's the likelihood that the 4th couple would be the first one that says they got divorced for incompatibility? That'd be waiting until the first success. The other model is called the binomial model. That one is number of successes out of a number of trials. How many trials here? How many couples are we looking at? 4. And this is going to be weird, but how many successes? How many are saying they got divorced for incompatibility? 2. So this is a binomial model. All right? So we're going to go to the calculator and do it. I'm going to write down my formula here. It's been a long time since you've done this. Let's see if I can explain this to you. Do you guys see why I put 0.65 squared? Why did I put 0.65 squared? Because this is the likelihood of them saying it's because of incompatibility, right? And it happens twice. Why did I put 0.35 squared? Because the other 2 couples, right, are saying they got divorced for some other reason. Okay? Do you guys see this here? This is called the choose function. Do you know why this is here? Because do I know if it's the first 2 couples? Could it be the last 2 couples? Could it be the middle 2 couples? Could it be the first and the last? Right? So there are a certain number of ways, right, of combinations that this could happen. All right? Correct, yes. And you can it includes something called factorials, which we did last semester. But honestly, Diana, to do this question, I would just use the calculator. All right, I would hit second vars and scroll down to binomial PDF, because it's exact. Letter A, you guys see letter A where it says binom PDF? Letter A. Second vars, Thomas. Okay, how many trials? How many couples? 4. What's my probability of success? 0.65. And how many couples are we saying are going to divorce because of incompatibility? 2. So this will give you the answer. 0.311. All right, last one, and then we're going to do the free response. We'll see if we can finish. We're really close. Okay, this one says, you toss a coin 10 times. Oh my gosh, Carolina, we're back to tossing coins. All right, it comes up heads every time. I almost did that. Eduardo, I don't think you were in here yet, but I tossed 6 in a row, 5 in a row, heads. It was amazing. Which of the following is a true statement? By the law of large numbers, the next toss is more likely to be tails. Another one? No. Keep going. It's Miss Render. Hello? Okay, you got it. Thank you. Carolina, you're out. I'm hoping you get to E and you see the E is the answer. Right? It doesn't matter how many heads you got in a row. The likelihood of you getting a heads on the next one is 50%. All right? All right. Do you think we can finish?
Yeah.
All right, we got this. Let's take a moment. So Carolina, watch the last few minutes of this for the free response question. Let's take a moment and add these up. This is 200. What is this? 225. 135. Can somebody check my work here? Oh, no, that's not going to be right. That looks right? Okay. What is the probability that an applicant is less than 50 years old? So how many applicants do we have? Yeah, we have 360. And how many are less than 50 years old? 225. So we get 0.625. I know I'm going super fast, guys. I'm just trying to finish. What is the probability that an applicant has more than 10 years experience? So more than 10 years. So that's 70 out of 360. .194. What is the probability that an applicant is more than 50 years old and has 5 or fewer years experience? So what is this? More than 50 and 5 or fewer. Is that 10?
Yeah, that's and. Would that matter?
Well, I think this or is not like the or you're thinking. That or is because it's 5 or fewer. That's why. But that's a good point. This really the key one is and. Good thought though. So this is 0.028. All right, letter D. Letter D. What is the probability that an applicant is less than 50 years old, given that she has between 6 and 10 years experience? So go to your table. I'm looking at between 6 and 10 years of experience. That's 200 people. And I'm looking at less than 50 years old. So 125? All right. So you can probably do that one in your head. 0.625. All right, and the last one. We did one just like this in the multiple choice. So let's pick one. Do you want to pick less than 50 years old or more than 10 years experience? You want to do that one? Okay, sure. All right, so this is more than 10 years. All right, so go to the table. That's out of 360. How many have more than 10 years experience? 70? Did we calculate that one? I think we did, yeah. So that's no, we did. Yeah, we did. 0.194. So now you copy it again, right? Write it again. More than 10 years. But now what's my given? Bless you. What's my given going to be? Less than 50 years old. Okay? So I go to my table, go to less than 50 years old, which is 225. And from that row, how many have, I already forgot, was it more than 10 years experience? Yes, so it'd be 20 out of 225. Oh no, I missed it too. My computer's about to die. 0.09. Do those match? No. So are they independent? No.